Morning. This is the smallest class of the semester. Did I cancel class? All right, we learned about absolute configuration yesterday, and so now I want to apply it to the molecules that I have here. But I also want to take an opportunity to go back to one of our molecules from the front and add absolute configuration. I want you guys to be able, kind of like with the chair conformations, I wanted you to be able to take the top-down view and draw a chair, or take a chair and draw the top-down view. I want you to be able to do the same thing with absolute configurations. Draw an absolute configuration as needed, and also identify an absolute configuration. All right. So let's take, well, if I could say that name, I would. Let's take the structure on the far left. So you guys remember me talking about the significance of chirality on methamphetamine's chiral carbon, right? One configuration makes the molecule incredibly addictive. One configuration has nasal passage impacts.
I just a question about the molecule.
Tell me.
So when it has that bold line, does that indicate that that entire half of the left molecule is coming at us?
Sure. Yeah, it's saying, well, you see that it starts from the carbon and it goes to the nitrogen. So it's just saying that whatever the group is bonded to that carbon is facing towards you, not away from you. So this molecule was used in the 50s to help treat morning sickness during pregnancy.
It's in Billy Joel's song.
It's in what?
Isn't it in Billy Joel's song that we didn't start the fire?
He talks about
thalidomide.
Yeah. I didn't know it was in We Didn't Start the Fire.
It's one of the lyrics, I think.
Interesting. If you find that, share it. Share it with me. Okay, so thalidomide. This compound was prescribed to treat morning sickness. The problem was only the R absolute configuration cured morning sickness. The S absolute configuration caused cancer and birth defects. Not cancer, tetragens. Carcinogens cause cancer, tetragens just cause other types of bodily defects. So, dangerous. If you don't actually separate out the two different configurations of this molecule, you could be killing people. And on the plus side, you might just be alleviating morning sickness. There's other versions of molecules like this. So methamphetamine is one. This molecule is another example where the configuration matters. There's other compounds, some that have been extracted from plants that show anti-cancer properties. And then the opposite configuration causes cancer. So let's figure out, is this the tetragen or is it the sedative? Will it help with morning sickness or will it create a birth defect? Is this an R absolute configuration or is it S? I want you guys to work on it. Report back. There's literally a 50-50 shot. And actually a multiple choice question on this could say, the chiral center is R, the chiral center is S, the chiral center is neither, or the chiral center, there's no way to know.
Okay.
And we can go with that. Think about that.
There it is.
Wow. Little Rock. Oh, that's a long verse. I don't want to read it. Uh, huh. Children of thalidomide. Yep. And he rhymed it with nothing. None of that. Oh, he rhymed it with homicide. Starkweather homicide, children of thalidomide. Huh.
I knew it. I was like, I know what this molecule does.
That's crazy. You recognize it just by its name. There's the rest of the class. Good morning. Oh, gross. Oh, you should have told your physics professor to come over. We are looking at thalidomide, which you know the history. Do you want to say it? They already know.
One of them made birth defects and one of them didn't.
One of them cured morning sickness. So it was prescribed to pregnant women, and one configuration caused birth defects, the other just cured morning sickness. So on your worksheet, we're going to figure out, is this the R or S configuration? If it's the R configuration, it causes birth defects. If it's the S configuration, it cures morning sickness.
Images of the thalidomide babies are so sad.
Michael just showed us that in the song "We Didn't Start the Fire," he has a line that says "Children of thalidomide."
He does. It's crazy.
Crazy. Yeah, I didn't know that you guys were all going to know about it.
I was born after 2000s, but I'm not as naive as I seem.
It was.
I didn't need to hear that.
I learned about it in my in research ethics courses.
Yeah, research ethics would be a great place to learn that.
Yeah, my dad just loved rock.
That's how you learned about thalidomide is from reading Star Wars.
Exactly. That's literally how I learned it.
Seriously?
Yeah, I was like 8 or 9.
That's crazy.
And I was obsessed with this song. So there was a 19.
No, none of the options is both. It's okay. Neither, but there are times that you can have a chiral carbon and there's no way to know whether it's R or S. And there's times where you don't have a chiral carbon, so it's neither R or S.
So wait, it has to be chiral.
Please.
Want to figure out which one is the chirocarbon and then
What does it mean to prioritize groups by atomic mass at point of difference?
Mm-hmm.
What is that? The point of difference?
So actually with this chiral carbon, the group to the top is a carbon,
Right.
starts with a carbon, and the group to the bottom starts with a carbon.
So like here and here.
No, because that's not the chiral carbon.
Oh, right.
That's a,
So first you find the chiral carbon.
yeah, can you do that?
Yes, I just need to think about it.
Okay.
And then
Circle it when you find
This
it.
guy. No, because that has a double bond.
Good.
it would be none of these,
Um,
none of those, not that one,
no.
none of those.
Is it this one?
Yes, it is.
It is? Okay, wait. Oh, it's this one because this is connected to an oxygen group and there's a hydrogen and then just a carbon.
Good.
Okay.
So all the carbons are sp2 or CH2s except for that one carbon.
Okay.
So one group to the top is a carbon.
Yep.
The other group to the bottom is a carbon.
Here.
And so what takes highest atomic mass? What takes highest priority by highest atomic mass? Carbon or carbon?
Neither.
Right, so that's not a point of difference.
Right.
Now keep looking along those groups for a point of difference.
So where it's not a carbon to carbon bond.
Yeah, or until you can find
Carbon and something else, right?
until you find an atom that is higher priority. So from the top,
Then carbon.
yeah, there's hydrogens. I'm not going to pursue them because I see a carbon. From the bottom, there's an O
Yeah.
and an N. So now I'm comparing carbon versus oxygen.
And the O counts even though, because of it, it's this whole row.
Yeah, because that's the group. Great.
So we found the chiral carbon.
Good.
We counted to left and right, and this is carbon to carbon, but this is our higher atomic mass compared to here. So number 2, 3, 4. So is it S?
Prioritize the 4 groups. Don't prioritize along the groups.
But the 4 groups, so
Why did you even pay attention to the group at the top? Right? How did you get to 6 if we're prioritizing 4 groups?
I was just counting the carbons.
Yeah, you were.
But okay, so if it's just prioritizing groups, it would be these ones.
Many of those groups are not directly bonded to the carbon. The 4 groups bonded to the carbon need to get their priorities. So we're not just assigning numbers. Correct. Attached to the chiral carbon, what's the priority? What do you think?
I think it's S. 'Cause N is the primary, is no 1.
1.
The carbon with the O would be 2.
Good.
And then 3 would be the carbon without the O.
Good.
So it doesn't fall in line, but you just follow the 1 and 2 route.
1 to 2 to 3. Yep.
Oh, and then 4 would be the hydrogen, which goes away from you.
And because that's what we want it to do, the way that we determine the rotation is what we expect. Great job.
Okay, so going back to that idea.
Good.
We assigned it, so this is priority number 1.
Good.
2, 3. And then this implied hydrogen is 4, which is our back.
Perfect.
Implied it's backwards. But how does that tell us whether it's like clockwise or counterclockwise?
So it goes from 1 to 2, so they
Oh, 1, 2. So it is still counterclockwise this way.
Good.
So it is
Yep.
the tetragen version. The bad version.
Right. Don't give that to your kids or your wives.
Or if the nitrogen was dashed, it would be an R.
If your lowest priority group is on
The second
a dash,
second heaviest.
No.
no?
If the lowest priority group is dashed,
I mean, if
that's
it's,
the goal.
yeah.
Okay.
Opposite.
If it's on a wedge,
Then you switch.
then you assign it opposite of what it looks
So you
like.
want your H's.
Wait, if it's on a wedge, you assign the wedge?
If the lowest priority is coming forward.
So it's not S, it's R.
No, if the lowest priority.
Remember, the rule was put the lowest priority back.
Which we already did.
Yes. Yes. Okay, so you guys agree on
On S.
S. Okay. So don't take it.
Yeah.
Don't create children of thalidomide.
Yes.
Right. Research ethically. What did that? How did that come up? They had investigated that something worked, but they didn't understand that there were 2 different versions well enough. Interesting.
If there's multiple chiral carbons,
Mm-hmm.
do each one get assigned in one their sort of
Mm-hmm.
Not
Yes.
as a whole, but
Yep.
independently.
Yes. They do. And then a molecule as a whole. We'll talk about that today too. The molecule as a whole can be determined as something as well.
So if it's like majority is counterclockwise, it'll overall be called counterclockwise.
No.
So there could be like one that's
There's no relationship.
so on the same.
Yeah. So we would use our locants to describe where the configuration is in the molecule. We'll talk about it, but there's no relationship between specific chiral carbons and the way that we refer to the molecule as a whole.
Oh.
Very strange.
Are there, if I were in your lab, would we be able to synthesize thalidomide?
No. Because obviously one version of it is a tetragen, so I'm not going to have you work with it. Also, to make those amides is not easy, so I'm not interested in it.
The distilling lab that we have, did we just distill shine or labs or no?
Do we still?
Do we, is there still a possibility to distill in shine or labs or no? So it just needs an
So we used to have an OChem 1 lab experiment where we mixed sugar and yeast and pasture salt solution to feed the yeast, and we created alcohol. We fermented the sugar into alcohol, ethanol, and then we took that the next week and we distilled it and we tried to separate the ethanol from the water. So that was the experiment. You guys did the experiment this week on distillation, but that used to be the experiment on distillation.
That's kind of sick though. Like ethanol is a good. I mean, it's a fast burning energy source.
Well, obviously, like it's in a lab using glassware from the lab, so we toss it in the waste at the end of the day. And you cannot eat anything that comes out of a chemistry lab. But I had some faculty that were like, I think this is illegal, that we have them distilling alcohol. And I was like, it might be illegal if they drank it, but they'd also fail the class. It might be illegal if they sold it, but they'd also be kicked out of the college. So it's not illegal to distill ethanol. That is just a physical phenomenon that you use an apparatus for. It becomes illegal if you're selling it or making money off of it without a liquor license, right?
Yes.
No, but in our labs, it would actually be a lot harder to do real distillation. We need a better apparatus. So what did you guys decide on? S? Okay, so for our chiral carbon on thalidomide, highest priority group was the nitrogen attached. The lowest priority group was the hydrogen that was dashed. So I'm just going to ignore the hydrogen that's dashed because it's where I want it to be. But then I look at carbon and carbon, and there's no difference. So I need to look at the next atom out in the group. And there's a lot of places to go. From the top, I could look at the two hydrogens or the carbon. Well, of course, I'm going to look for the highest priority group. On the bottom, I could look at the oxygen or the nitrogen. But I'm going to look for the highest priority group. So oxygen wins out over my carbons. And my rotation, 1 to 2 to 3, is counterclockwise. So this is our tetragen, the compound that will cause birth defects. Can you draw the sedative version? What would it take? Some wedge dashed magic. All it takes is having a dashed line up to that nitrogen, and it's done.
But you keep everything else in the molecule the same, like the
Placement of the oxygens, the connection of the structures, everything is identical. We call these stereo isomers.
So then, since that would be like the wedge, the dash at that point, we will just label that as 4 instead of 1 at that point, right?
Nope, the priority all stays the same.
It's still counterclockwise, but it's an R.
Right, because it's still rotating 1 to 2 to 3, but you're looking at it wrong. So take the opposite perspective, and now it's rotating R. Is this the only way I could have drawn the R configuration?
Probably not.
You could have flipped it like a pancake and then the wedge to the end.
Does that mean your oxygen would have to be flipped, right? If it was if it was wedged, then
So
oxygen would have to face the opposite way.
instead of flipping it like a pancake, because that just takes the whole molecule and makes it flipped over. What I did here was I mirrored it front to back. Things that were coming forward are now going backwards. I changed the position of two groups. You remember that's what we said changes the absolute configuration, is changing the position of two groups. I could have changed the position left to right instead, and Michael, this might be what you were trying to get at. But keep my wedge and dash together. Or sorry, keep my wedge in the same place that it is. This still has a wedged group, but this is now the R absolute configuration, 1 to 2 to 3, counterclockwise.
Likewise, I was thinking where that oxygen has that number 2, if that was in the number 3 spot and the hydrogen moved up, that would also be absolute R configuration, right?
Yes, I see what you're saying. So the two groups that you're thinking of switching are the two groups in the ring. Keep the wedge the same, but put the amides on the other side. Yep.
also be lead to an R.
Yep. So here's still priority 1, priority 2, priority 3. Still clockwise, still R. I see clockwise and counterclockwise all the time, all over the place. When I stir my coffee in the morning, we make 2 coffees at the same time. I always stir one clockwise, and then I do the mirror image on the other. I don't know why. Just can't help it. So this is the only one that looks like it's going counterclockwise, like it should be S, but I'm looking at it wrong. It's actually R. Because I broke the perspective rule. I'm looking at it backwards. So my perspective of clockwise and counterclockwise is backwards.
So you never want to go off of any of this based on any wedge or dash. You want to just do the right steps.
Just follow the
Can't
rules.
make any assumptions about it. It's a dash, so it's this, or it's
Yes, correct. Yeah, you can't ever look at a wedged chiral carbon and say it's R, or a wedged chiral carbon and say it's S. It cannot be determined that simply. Great. All right. You guys have more molecules there to practice. What I want to do is actually take you back to the front page and look at the Thank you. Iopamidol. And I want us to add absolute configuration to the one and only chiral carbon such that it becomes an R configuration. Does that make sense? I want us to create. Okay, actually, sorry, let me talk to you about these 4 options that I gave earlier. There were 4 options that I gave you for the absolute configuration. I said that the absolute configuration could have been R, S, neither, or no way to know. And all of those are valid answers depending on the carbon I give you. If I ask you about this carbon and I say, what's the absolute configuration? Is it R? Is it S? Is it neither? Or is there no way to know? So Michael and Elvira, I think, are saying no way to know.
Actually, it would be neither because this is for chirality, right?
Saray is saying it's neither. It's an achiral carbon. It is not S, it is not R, and we can know that because there's 2 identical groups. This is neither. That would be the correct answer.
So any achiral carbon is neither.
Right. All achiral carbons are neither R nor S. That's ridiculous. And it's kind of like taking those mittens that are not designed to be on one hand or the other, and they are actually symmetric and they can go on both, achiral. Saray. Where? Oh. Oh, I shortened my chain. Oh, I see. I thought they were just the same carbon group. Thank you. So it's an NH. And all the same, right? All of those other carbons were achiral. All right, if I had asked that question up here, what is the chirality? Is it R? Is it S? Is it neither? Is there not enough information? Or no way to know? No way to know / not enough information.
I would say, I don't
You do on the front page.
Because that hydrogen would be coming up.
Because if we assigned it dash coming down, then that was our priority.
Yeah.
priority.
So you need dashes
From a
to
break
be able to
perspective,
tell.
but if
Yeah.
it was one and it was wedged, then it would be clockwise.
If you assume something is wedged or dashed, you'll make an ass out of you and me. I don't know if that alcohol is wedged or if that alcohol is dashed. There's not enough information. It is a chiral carbon, so it's either R or S. It's not that it's neither R or S. We don't know what configuration it's in. Do you guys agree? What's your ruling?
For this one? S.
Why? Because the lowest priority is wedged or dashed.
I don't see any wedges or dashes.
So how can you assign R or S? If you don't know whether the lowest priority is coming towards you or away from you, you don't have enough information to make an assignment. You cannot assign chirality if there's lacking information, not enough information. All right, now I want to change that. I'm going to just re-simplify the structure. I'm going to just focus on this part that has the chiral molecule, this chiral carbon. And I want us to draw the absolute configuration or draw the stereochemistry that gives it an R absolute configuration. We don't have the stereochemistry yet, but I want to add stereochemistry to make it R, which generally means you're either going to make the alcohol wedged or dashed, although in theory it could be any of those three bonds. Something needs to become wedged, something needs to become dashed. It's up to you to decide how. A foolproof way would be guess and check.
This is how I would do it, because I would just automatically assign carbon, like our hydrogen coming off the carbon is our lowest.
Okay.
And just clockwise that way, as being the larger.
Why? Why is it the higher priority group?
Because it has more atomic mass.
Oh.
The oxygen.
But it's not a sum of all mass. It's the highest atomic mass at the first point of difference.
I see. So that would make it the hydroxyl then, or that alcohol.
The oxygen. The oxygen becomes the highest priority, regardless of what's even bonded beyond the oxygen.
Fourth's always going to be.
So I think I have like a fundamental lack of understanding
Oh.
here. So because we're assigning priority by atomic mass
At the first point of
the
difference,
first point of difference, which is here.
from there,
Well,
from the
sorry,
chiral carbon.
From here.
Yep.
So the first point of difference would be this nitrogen.
Yep.
And
Nitrogen is higher mass than carbon, or hydrogen.
okay, so nitrogen is higher mass than carbon.
Nope, that's your chiral carbon.
Carbon.
Good.
Carbon.
Your chiral carbon will never be a priority group.
Okay. And so nitrogen has higher priority than this group.
Because nitrogen is higher mass than carbon.
It's higher mass than carbon, not higher mass than oxygen.
Doesn't matter about the oxygen,
Oxygen doesn't
because that's
matter.
too far away.
There it is.
Good, good. Sorry, my brain just sometimes takes a couple of minutes or hours.
So if I'm running 1, 2, 3
Yes.
counterclockwise, I need my OH to be dashed to be R. Yeah.
Good, because
Because
regardless,
my
that
priority group 4 is forward, so
Yeah.
I'm flipped backwards.
that rotation is going to look counterclockwise no matter what.
So if you number your guys and you're like, oh my god, I'm trying to make an R, but I'm counterclockwise, then you know that your 4th priority group has to come out.
Good,
Okay, cool beans.
good. You got that too? Awesome. Michael? Good. Take some practice, huh? Yes. Yes. Andrew, you feel good?
Okay.
That worked. So what you did was drew a different conformation. You just moved the groups over so that you could create a wedge and not, but with this, we could have just made the OH dash. and the only difference is
Together.
configuration.
Does an absolute mean that the R has to be clockwise, or can you have an absolute R that is counterclockwise?
Well,
So would you need to flip it?
would you say that this is an absolute configuration where the R is counterclockwise?
That's what I'm asking. Is that the definition?
Can you ever have a left hand that is a right hand? No. But depending on your perspective, if you're just following the rules, then the perspective can impact that. So when the lowest priority is back, clockwise is always R. But when the lowest priority is forward, R appears to be counterclockwise, but you broke the rule. So it is still a clockwise R.
Configuration, but is it an absolute R configuration?
It is an absolute R. And that's why we call it absolute. Regardless of the perspective, and these are 3 different perspectives of the same absolute configuration. Regardless of the perspective,
Regardless of whether it's dashed or as long as you've got everything matches appropriate.
yep, it's absolutely R, it's never S, but the rules help us reason that out.
Let me do this, Professor. I thought number 4 always had to be dashed. Is that
That's our rule. That's like, remember the rule about how can I tell if it's my right hand or left hand? The palm always has to be away. And then thumb to pinky clockwise is the right hand, thumb to pinky counterclockwise is the left hand. The palm always has to be away. So what hand is this? Thumb to pinky is clockwise, so it's my right hand? Because my perspective is wrong and I broke the rule. But if we know that that happens, we can just correct for it. We can recognize that we're looking at the perspective wrong. So you can assign configuration even if the lowest priority comes towards you. But you have to know that you're breaking the rule to be able to recognize this looks like it's S, but my lowest priority is not coming towards me, so I'm looking at it wrong. It would actually be R. Go step into the room behind us and look at this dotted green line. It rotates clockwise. Go sit on the face of the clock with the numbers. The hands rotate counterclockwise. You get on the other side of a rotation, and the rotation changes. Did that answer it, Gavin? No. Okay, you're gonna have to keep working with it then. Keep practicing. The rule only works when hydrogen faces away. But you can manipulate the rule if hydrogen faces, not just hydrogen. Hydrogen's not always the lowest priority. The lowest priority, when the lowest priority faces away, you can still, okay, let me try and give you this example, Gavin. Here's a chiral carbon. High priority, second highest priority, third highest priority. Hydrogen, lowest priority is facing away. So 1 to 2 to 3, clockwise, R. Now what's the absolute configuration?
So it should be S, right?
Counterclockwise R.
Because
What hand is this?
your left hand.
What hand is this?
Oh, it's still the same.
Still your left hand.
Okay. What configuration is this? R.
R.
What configuration is this?
But if you
Still R.
It's an absolute configuration regardless of your perspective on it. We've set a system of rules to decide whether we name it R or S, and this always follows that system of rules.
But if you flip that yellow boy around, then you.
If I break the bonds and reconstitute the bonds, yeah. So how can I prove to you, Gavin, that this is R when I'm breaking the rule and I'm putting the lowest priority towards you? Because now it looks like 1 to 2 to 3 to you looks counterclockwise. But I just proved to you that it was clockwise, and now it looks counterclockwise because your perspective is wrong. So if you recognize that your perspective is wrong, you can just account for that. That was my tip number 1 yesterday. If the lowest priority faces forward, assign it opposite of what it appears. Know that you're looking at it backwards. Or just go through that extra work of rotating it into a new conformation or drawing the molecule after it has been flipped like a pancake and make it follow the rules. All right. So first thing to do here was assign priorities from the chiral carbon. What priority does the chiral carbon get? It's our reference point. We want 4 priorities relative to the chiral carbon. Oxygen is the first. Carbon bonded to oxygen is the second. Carbon bonded to hydrogen is the third. And then my 4th priority is not wedged or dashed right now. I need to decide, does my lowest priority need to be wedged or dashed in order to make this R? And when I look at this, it looks like it's going to be an S configuration if the lowest priority is back. I don't want the lowest priority back then, because I don't want an S configuration. So I want the lowest priority forward. For me, that means I'm going to make the OH dashed. It still looks counterclockwise, but I'm looking at it wrong. You guys have the freedom in the exam to stand up and do this if you need to, but I don't think you will. Also, it's really hard when you're the one doing it because it never changes for you. It's easier when somebody else does it for you.
Can we ask other people to do it for us?
No talking during the exam. Now, Andrew solved this because I don't think Andrew wanted to put the highest priority forward or the lowest priority forward. So Andrew solved this by redrawing it. And he went from a zigzag to a zig-zig. Here's my zigzag. And then he made a zig-zig. And you know what happens when you rotate a conformation from zigzag to zig-zig? Things that are forward move backwards. Things that are backwards move forward without changing absolute configuration. Priority 1, priority 2, priority 3 looks clockwise. Is what I want. Put that group wedged, which makes the lowest priority dashed. These are the same absolute configuration. They're the same molecule. The only thing that's happened is a conformational change. I've just rotated from zigzag to zig-zig, and so my OH now appears forward. My H now appears backwards.
Why couldn't we just draw the OH as wedged the first time?
There's nothing wrong with starting with that. Let's just say, I want this to be wedged. Done. Is it our configuration? 1, 2, 3. 1 to 2 to 3 is counterclockwise. It is not our configuration. Easy.
That was just an example.
Flip it to be dashed. Guess and check, right? I'm going to guess that maybe the OH is wedged. And the problem that I gave was draw the chiral carbon such that it has our configuration. So I guessed that maybe it will have an R configuration if the OH is forward and the H is back, and I guessed wrong. So now it's as easy to change as just making that OH dashed. Because when I swap two groups, I swap the absolute configuration. All right, there are some more practice problems on absolute configuration. And some of them highlight how counting your groups, prioritizing your groups, can be a little challenging at times. So I wanna walk through these ones with you guys. How many chiral carbons in acetic acid? I'm sorry, ascorbic acid? 1 chiral carbon. So let's try and prioritize our groups. Relative to my chiral carbon, highest priority. What's wrong, Delaney?
I thought it was the other carbon.
You thought it was this on the left? Oh, you're right. There are 2 chiral carbons. Unless I drew it wrong. No, you're right. There's 2. I just didn't give any stereochemistry to the other. Sorry. Thanks for pointing that out. You're just on top of it. All right, so ignoring this chiral carbon, which we don't have enough information to assign R or S, let's assign R or S to this chiral carbon. What's the highest priority group? The oxygen. And then the second highest priority group. This carbon branches to an oxygen. This carbon also branches off to an oxygen. It has more groups. Not only does it have that oxygen, it has another carbon. Or beyond that oxygen is a hydrogen to the left. Beyond that oxygen is a carbon to the right. Good. So again, we go as far as we need to determine the point of difference. This appears to rotate counterclockwise, but we broke our second rule. Yeah, we broke a rule. We broke the perspective rule. Do you agree, Gavin?
Yeah.
Okay, so although it looks S, the absolute configuration here is R. Do you guys understand what I'm saying when I put this in quotation marks? It appears to be a counterclockwise rotation, but I know I'm breaking a rule. So what it appears to be is opposite of what it actually is. All right, then.
I'm confused why our carbon attached to OH is 3 and not 2, because isn't that closer to OH than the other second carbon is?
So first of all, it's from the chiral carbon, I have a carbon and I have a carbon. Actually, let me show you this. Here's my chiral carbon. If I go out in one direction, I have carbon. If I go out in the other direction, I have carbon. Right. And this is ignoring the oxygen and the hydrogen. Okay, those are the same, not a point of difference. If I go to the left, my next highest priority is O. If I go to the right, my next highest priority is also O. Not a point of difference. And I can actually make 2 judgments here. I can either go past the O again and look at the H, and past the O again and find a C, in which case carbon is higher priority than than hydrogen. I could have also come back and finished these C's. Both carbons have 1 hydrogen attached. 1 carbon has a hydrogen versus a carbon. Once again, just reaffirming that group on the right is my higher priority. All right, then we have limonene.
What would you do if the C on the left had a carbon?
Well, you won't have to worry about it.
Okay.
I think ascorbic acid is one of the harder ones to assign.
Okay. Not as difficult as we'll ever see it.
Right. I'm not going to give you something that is quite that challenging. I like to know that you can follow the rules without having to push the limits of the rules. every chiral carbon in a molecule has its own configuration. Different from conformation. There's no such thing as an absolute conformation. Conformations by nature are different ways that they can take up space. But configuration is how they are taking up space relative to a stereocenter.
Can we say if our number one priority group is dash, that we can reverse, like we would have the opposite answer of what it looks like?
Yep.
Consistent?
If our highest priority was dashed, it would be an S.
So is that consistent, I guess, always opposite of what it looks like then? If our highest priority group is dash?
Not if your highest priority is dashed. Because our rule with perspective, remember with hands, the rule was palm. Put your palm away. It didn't say put your thumb in a specific spot. It said put your palm away. Our rule with chiral carbons said put the lowest priority dashed.
Right.
It did not say anything about the highest, the second, or the third priorities. So we can only pay attention to where the lowest priority is. What I mean to say there is it wouldn't matter if this had been the first, second, or third priority group that was dashed. What matters is that the lowest priority is wedged.
Okay, so if our lowest priority is always wedged,
It's always
it's always
opposite of what it appears. Perfect. All right, limonene has no heteroatoms. So we're going to have to go by carbons. From our chiral carbon, we have a secondary carbon, and a carbon we can't really say is tertiary because it's part of an alkene, and the number of carbons it's bonded to is debatable. Are we counting how many carbons uniquely it's bonded to, or are we counting how many bonds to carbon it has? But we can say that the lowest priority is dashed. All right, well, this carbon is bonded to 2 carbons, but it's bonded 3 times to other carbons. So when assigning priority, we count multiple bonds multiple times. So once again, here's my chiral center. I can go to carbon, carbon, or carbon. Sorry, let me actually show. This looks a little bit more reminiscent of what we have here. At the top, I can read this as carbon, carbon, carbon.
The star is the chiral carbon.
The star is the chiral carbon. So this group to the top has a carbon bonded 3 times to carbons. So I can count all 3 of those. Whereas on my other 2 sides, I have 2 bonds to carbon. So, oh no, I'm sorry. 1 bond to, beyond, sorry. 1 bond beyond. So the group on top has the most carbons, which means it's going to win the highest priority at some point. So this is priority number 1. We know that these are equal priority, and as we move past it, we run into a very similar situation where this is bonded fewer times to carbon, and this is bonded more times to carbon. 2 to 2. So we said these were not points of difference, those first carbons off. But then to the left, we get 2 bonds to carbon. To the right, we get 1. This wins out. This loses. Lowest priority is already where I want it to be, so I have an S absolute configuration. Tell me. Oh, Delaney.
So say there were single bonds, then we would go by size.
It's always atomic mass, and it's never a group's atomic mass. It's always an atom's atomic mass. But if you're saying if this whole structure only had single bonds,
Yeah.
like this. There's no chiral carbons anymore because now there's a plane of symmetry through that molecule, through those carbons. Okay. All right, we need to move on because it's not just about chiral carbons. Chiral carbons feed into chiral molecules. So chiral molecules have at least one chiral carbon. They absolutely can have more than one chiral carbon, but they have to have a minimum of one chiral carbon. Because they have at least one chiral carbon, they have zero, well, I'm actually going to say they lack a plane of symmetry. There's going to be a part of the molecule somewhere that doesn't reflect into a part of the molecule somewhere else because of that chiral carbon. So they'll lack symmetry. Obviously, asymmetry is chirality. We have another classification, which is achiral molecules. These have 0 chiral carbons and have at least one plane of symmetry. But this is not always true of all achiral things. There's actually a subset within achiral called meso. Meso molecules have at least 2 chiral carbons reflected by a plane of symmetry. They are achiral because they have symmetry, but they have chiral carbons, which is different than something that is purely achiral because it lacks chiral carbons entirely. Sorry, that's okay.
Why is it pronounced miso and not meso?
It might just be me. I don't know. Just how I've heard it in the past. No, that's a good question. I don't know. It might be meso. I've only heard it meso.
So does if it has to have two or more chiral carbons, but those have to reflect each other in some way.
They have to be symmetric.
If it has more than 2 but they're not symmetric, then it is not meso, it's chiral.
Yep. All meso compounds are achiral, but not all achiral compounds are meso. You got one? Sorry. So you should be able to go through and apply this to the compounds we had on the front page. Acetaminophen, achiral, 0 chiral compounds, 0 chiral carbons. Ibuprofen, chiral, because there's 1 chiral carbon. And threonine, chiral, 2 chiral carbons, but they definitely cannot reflect into each other. 1 chiral carbon has an NH2, 1 chiral carbon has an OH. Those will never reflect, so it has more than 1 chiral carbon. Dexamethasone, chiral, lots of chiral carbons, definitely no plane of symmetry. Iopamidol, I said it better that time. I said it faster anyways. Chiral, 1 chiral carbon only, so it must be chiral. Fentanyl, achiral, not meso. It's not. Fentanyl is not meso because it has 0 chiral carbons. Oh, so you're saying it's pronounced what?
It's meso, I looked it up.
Meso.
Like Mesopotamia.
Oh, Mesopotamia, what, and how does meso apply there?
Meso, it's the same.
Yeah, but what does meso mean in Mesopotamia?
Middle.
Middle of the earth.
Mesotropes, yeah.
Methamphetamine, chiral, achiral, or meso? I'm sorry, I'm just going to call it meso. Miso soup.
Yeah.
Me so sorry. Methamphetamine, chiral, 1 chiral carbon. What about thalidomide? Thalidomide, chiral, achiral, or meso? Chiral, only 1 chiral carbon. Ascorbic acid has 2 chiral carbons, but they do not reflect into each other, right? In order to be meso, those 2 chiral centers or more have to reflect into each other.
And not just 2, like if there's 4, they all have to reflect, not just 2 of the 4, right?
Say it one more time. Oh, yes.
Okay.
If there are 4 chiral centers, then there must be symmetry across all 4. Not necessarily between sets of 2, but somehow in that molecule.
You can't say, oh, there's 4, but 2 of them are symmetrical, so it's meso.
Yep. Limonene, chiral, achiral, or meso? Chiral. 1 chiral carbon. Okay. Easy enough to look at a molecule and decide whether it's chiral or achiral. Meso is one that we're going to practice with. But I'll give you an example of a meso compound right now because there's one that will come back throughout the semester as just a very common OChem example. Here's a meso compound. Do you see the plane of symmetry?
Yeah.
Where is it?
The plane symmetry basically like at the carbon connecting the bromine there.
Like through this?
Well, just if you go going down between the. Sorry, I'm trying to explain it. Down that way.
This way.
Yes. Well, no. There we go. Yes, that way.
Okay, so if I take this as a plane of symmetry, what that means is I should be able to draw 1/2 from the other half. This is that first grade art project where you draw 1/2 of the butterfly and you redraw the other half across the plane of symmetry. Oh, maybe not. Okay. Doesn't look quite right. Any other takers? Through the middle. Okay, once again, I should be able to draw just half of the structure and then get the other half from it.
Because that's what we were talking about with the zigzag, right, where it flips and then.
Do you see why I introduced that so early? Because it comes back. Zigzag, zigzag. So this is actually not a plane of symmetry. Would you agree? I took 1/2 and I did not get this on the other half. Actually, what I needed to do was go through a rotation. I believe 120-degree rotation. I needed to rotate around that sigma bond, and I got here. The carbon on the left maintained its bond line position. It maintained its wedge. The carbon on the right changed its bond line position, and because of that, our perspective of the dash became a wedge. Zigzag to zigzag. You know what else we could do is test the absolute configurations to make sure that the absolute configuration is the same. On the left, my carbon has bromine, carbon to bromine, carbon. So that's 1 to 2 to 3, our absolute configuration. On the right, I have bromine, carbon to bromine, carbon, 1 to 2 to 3, looks R, is S. Looks R is S. If these two molecules are the same, then I should still find RS configuration. Here's R. Do you know what the mirror image of a clockwise rotation is? A counterclockwise, like when I'm stirring my coffee in the morning. So if they have that counterclockwise rotations, they should be symmetric. Again, this stayed R. Now I have bromine, carbon to bromine, carbon, 1 to 2 to 3 definitely is S. Because R and S are symmetric to each other, because because R and S are mirror images of each other, because R is the mirror image of S, clockwise is the mirror image of counterclockwise. We can find meso compounds by making sure that they have a combination RS.
Like within the molecule?
Within those two chiral carbons, we said the chiral carbons are reflected by a plane of symmetry. Those chiral carbons are reflected by a plane of symmetry if they are R and S. But if I have RR or SS, there's no symmetry between those. Clockwise is not the mirror image, a plane of symmetry across from clockwise. Those aren't symmetric. So RR would have been this. SS would have been this. Why did I draw an S? And those are not meso compounds. And they're not even the same compound. They have different absolute configurations. They're different from each other. Because remember, this wasn't a plane of symmetry. But by trying it, we actually found where the plane of symmetry was, and that it's actually just a rotation. But if you try doing the same thing here, try rotating something that appears trans. When we actually can reflect the bond line into each other, we see that the bromines don't reflect. One bromine wedged, one bromine dashed, those don't reflect into each other. Both bromines wedged, both bromines dashed, those reflect into each other.
So that middle green one is a plane of symmetry.
No, so that we were investigating this structure for planes of symmetry. We found none.
Why is that middle example not?
We tried this. Are you talking about this?
Yeah.
We tried finding a plane of symmetry here. So I just took what was on top and I drew what it would need to look like on the bottom to be a plane of symmetry.
Oh, and that's not what
That's just a totally different structure. And then we took this and we tried to draw a plane of symmetry, and we found it's not a different structure, but it's a different conformation.
So that middle one would be a plane of symmetry, it's just not what we...
Yes, it's also not legal. That having two wedged groups is not legal. Breaks the tetrahedral. Okay, so here's a tip for you. The plane of symmetry that must exist, two chiral carbons reflected by a plane of symmetry, must exist in at least one conformation. This molecule is meso despite not having a plane of symmetry in this conformation. But in this conformation, the plane of symmetry is there, so the molecule is symmetric. If it can rotate into showing you a plane of symmetry, then the molecule has symmetry.
So you use this as like a broad or like a common example. So does that mean we may often see these kind of zigzag with an appearance of trans and then can kind of
Later in the semester, we're going to do reactions, and I'm going to have you guys look at a product that looks zigzag and redraw it as zig-zig. Actually, it'd be more like this. Look at a product that is zigzag and redraw it as zig-zig to understand how the reaction actually occurred. Very trippy. Okay, so we can assign a carbon as chiral or achiral. We can assign a molecule as chiral, achiral, or meso. In fact, I'll talk about this next week, but chiral molecules have a very interesting relationship with light. Chiral molecules rotate light out of its plane. If you can provide a plane of light, meaning it's not just scattered all over like the light we have in this room, but it's one directional light. If you have it interact with a chiral molecule, it will rotate that light clockwise, or it will rotate that light counterclockwise, and it has nothing to do with the absolute configuration of the carbons. So limonene, we can say there's R and S limonene, but there's also plus and minus limonene, or L and S compounds. Those are descriptors of how it interacts with light, which has no relationship to its absolute configurations at all. Yes. It's not their fault that we have a system of figuring out how the carbon is arranged in space and that we know how it rotates light. It's not our fault that those two things aren't related.
But why do they have to both be S?
Yeah, I know. Okay. I wasn't in the room for that. You're right. All right, now I want to talk about molecular descriptors. Ways that we describe, oh, no, I'm sorry. That's actually what we just did. We've described molecules. I want to talk about molecular relationships. The first, I believe we've talked about, so this should be a review. Structural isomers or constitutional isomers. Same chemical formula, different bond connectivity. We talked about this with nomenclature. Structural isomerism is what nomenclature really gets at the heart of. Do I have 2,2-dibromobutane, or do I have 2,3-dibromobutane? But we're seeing now that atoms can be arranged exactly the same in the molecule, but be arranged differently in space. So we get stereo isomers. Same atomic connectivity, different arrangement in space. And there's two main descriptors. The same atomic connectivity, different arrangement in space.
What does that mean for chemical formula?
Same chemical formula. Yeah, same chemical formula. Okay, actually there is another type. I don't hit on this very much. There is another one that we can call conformational isomers. Which of course just differ by what conformation they're in. Those are the same molecule, they're just rotated differently around their sigma bonds. Stereoisomers are not conformational isomers. They have different absolute configurations.
So a conformational isomer is an umbrella, like under the umbrella of
No.
It's its own third category.
Yeah, third category. I just didn't want to do it in black because I felt like that would. When I have a subcategory, I do my little sub arrows. You guys, how do you feel about my arrows? I don't know what it is.
I think it's helpful.
Yeah. I don't do bullet points. I don't do dashes. I do arrows and sub arrows.
I think it's helpful.
Okay. If you ever get confused by it, don't hesitate to let me know.
You said the confirmation isomer said it was the same
That's a third category.
structure.
Yeah, so like an eclipsed conformation versus a staggered conformation, those are conformational isomers to each other. Same molecule, nothing different, just rotated around a sigma bond.
Did you say stereoisomers have different absolute configurations?
Different absolute configurations.
So that means
And relative, actually relative configurations as well. Cis-trans is stereoisomerism.
Okay, right,
Cis-trans is only relative though.
but it's not.
It's not absolute.
oh, okay.
It's not RNS.
I was going to ask if, like, with conformational isomers, if the chairs that we've been studying.
Chairs are conformational isomers. High energy conformer, low energy conformer.
You said, are structural isomers the same molecular formula but different arrangement of atoms?
Actually, all of these have the same molecular formula.
Okay.
Structure is same molecular formula, different atomic connectivity. Atoms are arranged differently. Conformational isomers, everything is identical, but it's just rotated around a sigma bond. Stereoisomers, everything is bonded the same except for their spatial arrangement, R versus S, or cis versus trans. So we can do that as a review. First, we have these relative configurations. We talked about cis 1,2-cyclobutane diol, but we could have had trans 1,2-cyclobutane diol. Those are stereoisomers, but it's just relative because the compound on the left is meso, so it's achiral, but the compound on the right is chiral, and that means there are two different ways for the groups to be trans to each other that are not the same. So relative configuration just says cis-trans. Absolute configuration has some more detailed descriptors. So let's look at our absolute configuration. If the stereoisomerism is in the absolute configuration, here are some of the names we give to them. Enantiomers. This is a relationship. This is like saying, oh, you're twins. No one would ever look at Kayla and say, oh, you're twins. What? But I might look at Kayla and her brother and say, oh, you are twins because you look so similar to each other. You'd never look at one molecule and say, wow, you're an enantiomer. You need two molecules to be able to describe a relationship as enantiomers. Enantiomers are non-superimposable mirror images. That's the jargon. Here's the way that we defined it. All chiral carbons swap absolute configuration. And by absolute configuration, I mean R and S. The enantiomer of methamphetamine is used in Vicks Vapor Rub. The enantiomer that cures morning sickness caused birth defects. My left hand is the enantiomer of my right hand.
So not two of.
Tell me again.
Not the enantiomer two, it's the enantiomer of.
I think those would be, yeah, the enantiomer to my left hand is my right hand. The enantiomer of my left hand is my right hand. I think two or of is fine there. But you need a relationship. You need two things. If you have only one chiral carbon, that's fairly easy to do. If you have multiple chiral carbons, every chiral carbon has to change. So look at the structures down here. I have lawsone, which I believe is the active ingredient in henna. Henna. Henna tattoos and henna dye. The ink. This is lawsone. How many chiral carbons? Zero. Good. Now, would you agree that this is a mirror image? The two structures are drawn as mirror images. Are they superimposable mirror images, or are they non-superimposable mirror images? If I slide them over as they are, they don't superimpose. But if I flip one of them like a pancake, then they superimpose. So, and yeah, actually, Michael, that's a great idea. I could literally just do this, fold my paper in half, and they perfectly superimpose with each other. Everything has a mirror image. Dr. Strange taught us that. Thank you, Dr. Strange. Not everything is superimposable with its mirror image. Some things are not. Okay? Lawsone is superimposable with its mirror image. So it is not, these two structures are identical. They are not mirror images.
So it doesn't matter if it's superimposable via slide or flip, as long as one of the two ways you can get it to match?
Any rotation, spin, flip, any legal change to get them to superimpose.
Because they're in 3D space, right?
Exactly. These are three-dimensional molecules. Achiral and meso compounds have no enantiomer. Because a meso compound is superimposable with its mirror image. We drew this meso 2,3-dibromobutane, and even if I draw the front-back mirror image, so now I get my two bromines to be faced backwards, just flip it like a pancake, and the two bromines go backwards. Meso compounds have a mirror image that they're superimposable with. So they are meso compounds never have an enantiomer because their mirror image is always superimposable. The other relationship that we'll talk about is a diastereomer. Now this one always trips up people on how to pronounce it, so I'd like you to repeat after me. Diastereomer. Diastereomer. Not diastereomer.
That's how I read it.
Diastereomer. You see the stereomer is getting at, mer means unit, stereo there again, talking about space. Dia, I actually like in the name because it should draw your mind to thinking about two things. No. First of all, diastereomers are non-superimposable, non-mirror images. They're not just reflections, but they still can't take up the same space. They're not the same molecule. So the way that we look for this, at least one chiral carbon swaps. at least one stays the same. In which case, some forward backward is swapping, or some left-right is swapping, but not all. They're not going to take up the same amount of space. In enantiomers, every chiral carbon swaps, whether that's 1, 2, 10, 1,000. Diastereomers have at least one chiral center in common, one absolute configuration in common, and at least one absolute configuration different. Not all not all chiral compounds have diastereomers. Methamphetamine has no diastereomers because there's only one chiral carbon. So if it changes configuration, it's an enantiomer. All chiral carbons have swapped. Sugar, we saw fructose on the front side of this sheet, has like 1 billion chiral carbons. I'm sorry, 1 billion diastereomers. Because there are so many chiral carbons that you could go through and put all of them as R, all of them as R except for one, all of them as R except for one but move it in, all of them, right? There are a lot. In fact, you can figure out how many stereoisomers you have. The number of stereoisomers is equal to 2 to the power of n, where n equals stereocenters, like chiral carbons, minus 1 per mesoform. Because if you have a meso compound, if you have any sort of meso stereo form, then it is symmetric to its mirror image, and that cuts down on how many different stereoisomers you have. I'm not going to have you guys use this a lot, but it is kind of useful. So we said fructose, no, not fructose, sucrose had 9 stereoisomers. So 2 to the 9. Hey Siri, what's 2 to the 9? My Siri doesn't listen.
Hey Siri. I guess mine doesn't either. Bad listening device.
It would be 64 times 64 times 2. So 64 squared and then doubled. What's the square of 64? Who knows? Because I did 2 to the 4th, 2 to the 4th. 512? Oh, that's smaller than I thought.
Well, that's 2 to the 9.
2 to the 9 is 512. So there are 512 stereoisomer forms of sucrose. 500 in different ways that you can arrange those chiral molecules in space.
But why? Like, why would you have different arrangements? Just because?
And yet life exists with very select combinations.
Yeah.
It's not why, it's how. How did those bonds form? When they formed, what arrangement in space did they form in?
Like, I guess I'm asking what the difference is between one.
Sometimes it can be nothing. Ibuprofen has 2 stereoisomers in enantiomers. Ibuprofen has 1 chiral carbon.
Right.
Both are effective at neutralizing your pain. Methamphetamine also has 1 chiral carbon, 2 stereoisomers. Thalidomide has 2 stereoisomers. And we talked about how different those effects can be. Because everything in your body, most everything, is also chiral. Remember that example I gave of a left-handed glove that cures cancer across the world? The left-handed glove that nukes the entire planet. Why? Who knows? But your body has all these chiral receptors, and based on how it's arranged in space, it might fit into a different receptor that does something different.
So enantiomers and diastereomers are under the umbrella of stereoisomers.
These are stereoisomers. Yep. Saray and then Andrew.
So are we just equating stereocenters with chiral carbons or chiral molecules?
We'll talk about more stereocenters, but chiral carbons are one type of stereocenter.
One of the homework problems says that there's two enantiomers. How can there be two non-superimposable mirror images?
That's the definition, right? Twins are always two. Triplets are always three. Enantiomers are always two.
It's an R and an S.
Well, it's a mirror image.
If they give you a molecule and say there's two additional.
You're talking about the last problem, right? And it's talking about a chiral receptor.
Yeah.
The question is saying this molecule has two enantiomers. I mean, that's by definition. The question is, which enantiomer are you looking at? That's what that question is getting at. This molecule can show up in one enantiomer form or the other enantiomer form. Which form are you looking at? It's not saying the molecule in question has two different enantiomers.
Yeah.
It's just saying the molecule has two enantiomeric forms. Which way are you looking at it?
Are you looking at 19?
No, this is 22.
Oh, yeah,
So it's asking you to assign the absolute configuration.
yeah.
And that would be the enantiomer you have, not the other absolute configuration.
Like we had like how we had it without any wedges or dashes is what it gave us, and then it says draw it as an R, and that assigned the wedges and dashes, or if it's
Thalidomide.
which way would they go?
Thalidomide has two enantiomer forms. One is a tetragen, one is a sedative. Which one do we have?
Oh,
That's almost exactly what that question's asking. It's not that this drawing has two additional mirror image forms.
yeah.
This molecule has two mirror image forms. Which one of those two am I looking at?
Okay.
I was gonna say enantiomer is opposite. I just looked it up.
Oh, nice. Anti, I guess, makes sense. Enanti. I didn't think about that.
Is that an example of an enantiomer right there, or?
They're mirror images, but they're not non-superimposable. They are superimposable.
Do we have
Yeah, we have examples. Oxycodone. Oxycodone there, I've drawn two enantiomers. Methamphetamine, I've drawn two enantiomers. What about 1,2-dibromo, 1,2-diphenylethane? What relationship do we have between those?
They have they're like, one's rotated.
One's rotated.
Symmetry, so it's
Conformational isomers. If you go through and apply the absolute configuration. Okay, what about this, this polymer bisphenol A? First of all, is that molecule chiral, achiral, or meso? Does it have chiral carbons? Can those chiral carbons be reflected into each other?
yes.
Right through the middle of the structure, those two chiral alcohols are reflected into each other. So this molecule is meso. So the mirror image that I've shown below, an up-down mirror image, is that the same molecule, or are those enantiomers? Same molecule. Because meso compounds have no enantiomer. Meso compounds are identical to their mirror image. What about geosmin? Geosmin is the chemical that we smell when it rains. Geosmin is actually there in the middle. What relationship does geosmin have to the structure on the right? Diastereomer. What relationship does geosmin have to the structure on the left? Also a diastereomer. What relationship do the two molecules on the left have, the left and the right have with each other? For geosmin, the far sides. You don't know?
Oh, they're
So we said the middle structure with the right is a diastereomer. The middle structure with the left is a diastereomer. What's the left structure relation to the right structure? Did all stereocenters flip their absolute configuration? Looks like that OH maintained its wedge position. So one stereocenter has stayed the same, more than one has changed. Diastereomers. None of the geosmin structures shown are enantiomers. They're all diastereomers to each other. And they all have their own enantiomer. Okay, down at the bottom, I want you to see how I have included the stereochemistry into the name. Actually, what I wanted you to do with the rest of these, I wanted you to draw the enantiomer of penicillin. I'm going to leave that for you to take home and do. I wanted you to notice that the sugars are all diastereomers to each other, but I also wanted to point out how the sugars now show us planes of symmetry in those Fisher projections. Notice the sugar on the far left that has all 4 of the OH groups facing to the right. We now know that those are all chiral carbons because they're all bonded to 4 different groups. Oh, actually it doesn't. Oh, I drew it wrong. I should have had a different group on the top or the bottom. Okay, never mind. They're all chiral carbons. And you can see that from the far left structure to the middle, 2 stereocenters stay the same, 2 stereocenters flip, diastereomers. And then to the right, 1 stereocenter flips, diastereomers, or relative to the front, 3 stereocenters flip, diastereomers. Gavin?
Non-superimposable means you can't slide it over and you can't flip it?
Right. There's no change that you can do rotating in space to get them to superimpose.
And dashes and wedges are different.
Because you can't break that. Okay, here's the deal. I wanted you guys to find your pairs in your molecules and decide whether you have enantiomer, diastereomer, identical, or structural isomer. So Andrew and Alvira and Delaney, you guys have this structures that relate. I want you guys to meet up quick before you leave and decide your relationship. Orange, Jacob, and Michael, decide the relationship on your compounds. Purple, Chloe and Gavin. Blue, Kayla and Patrick. And then green.
So there's either structural isomer, conformational isomer, or you go into the class of...
We're not going to do conformational isomer. You'll either have the same molecule, you'll have the enantiomer molecule, you'll have the diastereomer molecule, or you'll have a structural isomer.
They're not the same molecule.
I want to say this is diastereomer. There's no like flip that I can make without breaking and moving bonds.
Okay, good work. Thanks. Sorry for shocking you. Diastereomer,
I said diastereomer, but
meaning that one chiral carbon is exactly the same and one chiral carbon is different. Because I can't get either of your chiral carbons to line up.
so they would just be
Mirror images.
enantiomer.
Enantiomer. Do you see the mirror image?
Yes. Yeah.
And that they're non-superimposable. There's no enantiomer. Yep. Yeah. Think of that. Mer is unit, so it's enantio. Mer. Diastereo. Mer. You guys had enantiomers. You had non-superimposable mirror images. You guys think you got it?
If they are superimposable non-linear images.
That will take practice.
Non-superimposable, non-mirror images. If you have superimposable, then they must be mirror images still.
If they're superimposable, like for example, they go perfectly over.
identical.
Identical.
That's the same structure.
Oh, so basically that's,
They're not stereoisomers.
okay.
They're the same molecule. And I wanted to just show them on camera too. So these ones perfectly superimposed. Both chiral carbons are the same, which means that they are the same molecule. These are identical.
So they're neither in it.
They're not stereoisomers. What did you guys have? Great. I want to show that one on camera too. And you guys only had one chiral carbon, and your one chiral carbon is mirror imaged to each other, but non-superimposable. No matter what conformation you get into, can never superimpose them. Purple, what did you guys decide?
Structural isomer.
Why?
Because it's the same molecular formula, but it's arranged differently.
Right, that purple ball is on a different carbon. So they're not even stereoisomers, they're just bonded differently entirely. Green, what did you guys decide? Meaning identical? I disagree, because conformational isomers are identical structures that can be rotated into each other. You guys have one chiral center the same, but you have one chiral center that's opposite. So you have non-mirror, non-superimposable stereoisomers, diastereomers. One chiral, and notice how this form is meso, and this form is chiral. Meso compounds have diastereomers. They don't have enantiomers, but they have diastereomers. And in fact, they have two. Was that all of them? Okay, and I'm sorry to have to say this right as I stole so much time from you. I wanted you guys to decide which diastereomer of this dibromo ring is the one for which the name is given. So you have 1s, 2r, 3r, 1,2-dibromo, 3-methylcyclohexane. I want you to figure out which diastereomer has those chiral configurations. That was the goal there, okay? So you're just assigning configuration based on what they have and then figuring out which one agrees with that name. Okay, thank you guys for your time.